Similar polygons. Our objectives are to be able to use ratios and proportions to write and solve equations, and to be able to identify similar polygons and use them to find missing side lengths and angle measures. Let's begin by reviewing what are congruent polygons. Remember, these are where the angles are congruent and the sides are congruent. Remember the congruence statement, such as this one, to tell us that these triangles are congruent. Triangle ASM is congruent to triangle JRB. We can tell if we slide one of the triangles over top of the other triangle that yes, all the sides and the angle measures are congruent to each other. The congruent statement helps us to tell which parts correspond, such as when the angles are congruent, angle A is congruent to angle J. So for example, angle A is congruent to angle J. The sides can be shown which are congruent by noticing the two letters next to each other in the congruent statement. For example, side SM is congruent to side RB. If we take a look at the picture, we can count the blocks in the coordinate plane. 1, 2, 3 for side SM and 1, 2, 3 for side RB. So it is true that these are congruent because 3 is equal to 3. Let's count the other sides just so we don't have to do it by moving one triangle over the other. So these two, this side JR is 2 blocks and this side AS is 2 blocks. Now when it's a slanty side, we find it by using the Pythagorean theorem. Or we could grab our ruler, measure side JB. Notice that from the 0 on the ruler, it looks like it's about 25 centimeters. And then rotate the ruler and see how many blocks that is approximately. So according to the graph, it looks like the 25 ends just past 1, 2, 3 and a half blocks. So we'll call that side approximately 3.6 blocks long. Now, of course, if we take it and measure the corresponding side in the other triangle, AM, we notice that it measures to the same place on the ruler as well. So that side is also 3.6 blocks long. Now, what if we were to take triangle JRB and dilate it by a factor of 2? Let's check this out. So remember, to dilate means to stretch or shrink. So when I say by a factor of 2, well, this side going up and down was originally 2 blocks long. Now I've made it 4 blocks long. And the bottom side, which was originally 3 blocks long, is now 1, 2, 3, 4, 5, 6 blocks long. Well, I don't have congruent triangles anymore. Now what I have is called similar triangles. Notice that new triangle JRB has all the angles congruent to the old triangle. See how when I line them up, they fit exactly in that spot? And this angle right here fits exactly in that spot, except now it's twice as big as it was before. This creates similar polygons. Think dilation. So remember, when we took one of the triangles and matched up the angles, all of the angles matched. So therefore, in similar triangles, the angles must also be congruent, just like congruent triangles. But this time, the sides are not congruent, they are proportional. The sides are proportional, and that's different. So we still have a similarity statement that tells us which parts correspond, but notice that this symbol is not a congruent statement. Remember, the congruent statement has the equal sign under the squiggly, so you know more things are equal. But the similarity statement has just the squiggly because not as many things are equal. So the angles are still congruent, but now the sides are proportional. So we can still say, for example, that angle A is congruent to angle J, just like we did with the congruent triangles. But now the sides are proportional. For example, we would say that side AS as a ratio to side JR, these two corresponding sides, will be equal to side SM, this side, over its corresponding side RB. Notice we've made a proportion. A ratio equals another ratio. Well, what does that mean exactly? So remember, in the first triangle, this is 1, 2, 3 blocks, this is 2 blocks, and this was 3.6 blocks. Now we've got 1, 2, 3, 4, 5, 6 blocks, 1, 2, 3, 4 blocks, and if we took our ruler and measured, we would find that this is twice of 3.6, or 7.2. Notice when I measure that hypotenuse, it goes out to about the 45 centimeter mark, and when I rotate it so that it goes along the blocks, that 45 is 7 blocks and a little bit past. So 7.2 makes sense when we do it with the ruler method. So back to the sides being proportional, AS is 4 units long, JR is 2 units long, SM is 6 units long, and RB is 3 units long. Do those equal each other? Well, 4 divided by 2 is 2, and 6 divided by 3 is also 2. So they sure do. That's what it means that the sides are proportional. So we also have our proportionality statement. That is a proportion. It shows the ratio of the corresponding side lengths. That's what we just did here. It shows the relationships of the sides. And this is a proportionality statement for all of the sides. So it includes what we did, but also the third side, AM, over JB. Remember the word statements, like proportionality statement, similarity statement. We use statements in proofs, like we will be doing with these. Remember that when we dilated, we had a scale factor. That was our ratio. Remember the chart? Where does scale factor go? That's right, in the EE column. The scale factor is the ratio of the lengths of two corresponding sides of similar polygons. So in this case, 4 over 2 simplified down to 2 over 1, so 2 over 1 is the scale factor of those similar triangles. Let's take a look at some examples. State if the polygons are similar. If so, write a similarity statement, a proportionality statement, and the scale factor. So remember, to be similar, these triangles would have to have angles congruent, so that's what we'll ask ourselves first, and they have to have sides proportional. I'm going to abbreviate. Now I'm putting question marks because I don't know the answers to those yet. Let's take a look at the first one. Are the angles congruent? So I see this angle is congruent to this angle, and this angle is congruent to this angle, and by the third angles theorem, this angle is also congruent to this angle. So yes, they are. How about the sides? Are they proportional? Well, let's take a look. I see 3 different side lengths. I'm going to start with the smallest. I'm going to compare it to the smallest in the other triangle. So I'm going to say 6 divided by 4.5. What does that simplify to? If I have my graphing calculator, I can say 6 divided by 4.5, math, enter, enter, to simplify the fraction. That makes 4/3. So this simplifies to 4/3. Then I have the medium side over the medium side. 8 over 6 also simplifies to 4/3, and finally 12/9, the biggest sides, and that also simplifies to 4/3. So yep, the sides are proportional. So that means yes, we do have similar triangles. So what is a proportionality statement that can be written? That comes from the side lengths. So remember, we put the 6 over the 4.5. The 6 came from the MN side. So MN over the 4.5 came from the PO side. That equals these other ratios. The 8 came from the LM side, and the 6 came from the TP side. Last ratio, the 12 came from the LN side, and the 9 came from the TO side. Notice that when I do it, I try to make sure the angles match up too. So the L and the T are both marked the same way. Now the scale factor. Well, notice that all of these ratios turned out to be the same number. That's the scale factor. The similarity statement is now where we match up the corresponding parts. Triangle, I'll do the first one as LMN. It's good to go in alphabetical order sometimes. Similar to triangle, L matches with T, M matches with P, and then the last one is O. Let's take a look at the second one. So remember, we ask ourselves, are the angles congruent and are the sides proportional? Let's start by looking at the angles. Well, I notice there are no angle marks whatsoever. So no, the angles are not congruent. I could stop there and simply say, nope, they're not similar, therefore I can't do anything else. Notice if we check if the sides are proportional, little side over little side is 5/2. That doesn't simplify. And medium side over medium side, 12/6, simplifies to 2/1. And these do not match each other, so no, the sides are not proportional either. Let's take a look at one more example. Given the similarity statement, ABCD is similar to WXYZ, write a proportionality statement to show the relationship between the side lengths. Now notice we don't have all of the side lengths in the bigger polygon, but I don't need them. I've got the similarity statement to refer to. So side AB corresponds with side WX. So AB over WX equals, now look at another pair of sides, BC and XY. BC over XY equals, we're going to write all four sides, CD over YZ equals, and finally the last pair, AD over WZ. Notice that I'm always starting on the right, left, and going to the right, left to right, just like we read words. Now our job is to find the scale factor. We're going to do that by using one of these ratios that will have numbers, because the scale factor will be the numbers. The only thing in this polygon, the only side that has a number is side AD. So I'm going to use this ratio because that one has the AD in it. So that uses 14, AD is 14, over WZ, WZ is 10. So 14/10. That simplifies to 7/5, so that is the scale factor. Now we'll talk about how to find the values of the missing side lengths. Notice side AB. We don't know side AB, but we know that side AB corresponds to side WX. So I can say AB over WX says 8. So instead of WX, I'll write 8. And remember, all of these ratios are equal, so this equals 7/5. Remember how we solve a proportion? That's right, cross multiply. 5 times AB can be written as 5AB equals 8 times 7 is 56. Divide both sides by 5, so AB equals 11.2. Let's set up proportions for the other ones. BC over XY. BC we don't know, so we'll write BC over XY is what it corresponds to, and that says 4, and it equals the scale factor 7/5. Now we cross multiply. 5 times BC equals 4 times 7, or 28. Divide by 5, and BC equals 5.6. So I can write 5.6, just like I should have written in the picture for this side, 11.2. Let's do the last pair of sides, CD, which I don't know. Here's CD, but we know it corresponds to YZ, and that one says 3. And of course, what does it equal? 7/5, the scale factor. We cross multiply. 5 times CD equals 3 times 7, or 21. Divide by 5, and we get CD is 4.2. Determine the perimeter of each figure. Let's start with the figure on the left, ABCD, since we always work from left to right. So I'm going to do the perimeter, which just means adding up all the side lengths. I'll start with the smallest and move to the biggest. 4.2 plus 5.6 plus 11.2 plus 14, that equals 35. Let's do W, X, Y, Z. Again, starting with the smallest and ending with the biggest, just to keep track. 3 plus 4 plus 8 plus 10, and that equals 25. Part E, what is special about the perimeters of similar polygons? Notice the two perimeters. If I make a ratio out of them, 35/25, and I reduce it, it also makes 7/5. Well, why is that? Remember where perimeters go on our chart? That's right, the EE column. So think of your chart, and you'll be able to see these relationships a lot easier. Thanks for watching.